The top 10 equations that changed the world. The Fourier transform. The Fourier transform is an important image procedure which is used to decompose an image into its sine and cosine components. The output of the transformation represents the image in the Fourier or frequency domain, while the input image is the spatial domain equivalent. Schrödinger equation. Developed by Austrian physicist Erwin Schrödinger in 1926, his equation was a significant landmark in developing the theory of quantum mechanics. The equation is a type of differential equation known as a wave equation, which serves as a mathematical model of the movement of waves. It governs the behavior of atoms and subatomic particles in quantum mechanics. Today, all of our semiconductors, transistors, integrated circuits, Intel CPU chips, etc. depend on the science of quantum mechanics that wouldn't have been possible to understand without Schrödinger's equation. It also paved the way for nuclear power, microchips, and electron microscopes. The wave equation. The wave equation is an important second-order linear partial differential equation for the description of waves as they occur in classical physics, such as mechanical waves, for example, water waves, sound waves, seismic waves, or light waves. It arises in fields like acoustics, electromagnetics, and fluid mechanics. Chaos theory. Chaos theory concerns deterministic systems whose behavior can, in principle, be predicted. Chaotic systems are predictable for a while and then appear to be random. The amount of time that the behavior of a chaotic system can be effectively predicted depends on three main things: how much uncertainty can be tolerated in the forecast, how accurately its current state can be measured, and a time scale depending on the dynamics of the system, called the Lyapunov time. Some examples of Lyapunov times are chaotic electrical circuits, about 1 millisecond, weather systems, a few days, the inner solar system, 4 to 5 million years. In chaotic systems, the uncertainty in a forecast increases exponentially with elapsed time, hence mathematically doubling the forecast time more than squares the proportional uncertainty in the forecast. This means, in practice, a meaningful prediction cannot be made over an interval of more than 2 or 3 times the Lyapunov time. When meaningful predictions cannot be made, the system appears random. Maxwell's equation. Maxwell's equations are partially different equations that relate to the electric and magnetic fields, to each other, and to the electric changes and currents. Often the changes and currents are themselves dependent on the electric and magnetic fields via the Lorentz force equation and the constitutive relations. In mathematics, the logarithm is the inverse function to exponentiation. That means the logarithm of a given number x is the exponent to which another fixed number, the base b, must be raised to produce the number x. In the simplest case, the logarithm counts the number of occurrences of the same factor in repeated multiplication. For example, since 1000 equals 10 by 10 by 10 equals 10 exponent, the logarithm base 10 seconds of 1000 is 3, or log 10 1000 equals 3. The logarithm of x to base b is denotated as log bx, or without parentheses, log bx, or even without the explicit base, log x, when no confusion is possible, or when the basis does not matter, such as in big O notation. The second law of thermodynamics. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time and is constant if only if all processes are reversible. Isolated systems spontaneously evolve towards thermodynamic equilibrium, the state with the maximum entropy. The total entropy of a system and its surroundings can remain constant in ideal cases where the system is in thermodynamic equilibrium or is undergoing a fictive reversible process. In all processes that occur, including spontaneous processes, the total amount of entropy of the system and surroundings increases, and the process is irreversible in the thermodynamic sense. The increasing entropy accounts for the irreversibility of the natural processes and the asymmetry between future and past. Historically, the second law was an empirical finding that was accepted as an axiom of thermodynamic theory. Statistical mechanics, classical or quantum, explains the microscopic origin of the law. Einstein's theory of relativity. Albert Einstein, in his theory of special relativity, determined that the laws of physics are the same for all non-accelerating observers, and he showed that the speed of light within a vacuum is the same no matter the speed at which an observer travels. Newton's law of universal gravitation. Newton's law of universal gravitation is usually stated that every particle attracts every other particle in the universe with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Pythagorean theorem. According to mathematicians, the square of the hypotenuse of a right triangle is equal to the sum of the squares of the other two sides. And for number 1 in this list, I'll put calculus. The formula given here is the definition of the derivative in calculus. The derivative measures the rate at which a quantity is changing. For example, we can think of velocity or speed as being the derivative of position. If you are walking at 3 miles per hour, then every hour you have changed your position by 3 miles. Naturally, much of science is interesting in understanding how things change, and the derivative and the integral, the other foundation of calculus, sit at the heart of how mathematicians and scientists understand change.